In this video, we're going to be expanding upon our knowledge of what chemical reactions or chemical changes in general actually are. In the previous video, we defined a chemical reaction is any change that causes a significant change to the chemical structure of a substance, but we didn't really define what chemical structure actually was, so that's the first thing that we're going to do here. We can see that we have a chemical reaction. These are the reactants that we start with, and these are the products that we make. And this is actually a fairly common reaction that most people have seen at least once in their day-to-day life, whether they knew it or not. This rather complicated chemical formula, CH3COOH, is actually the acid that we find in vinegar, the sour additive that is normally added to food in certain styles of cooking. And we can see that when we put it into water, it undergoes a change to its chemical structure. Now, we can't see this change if we just look at the chemical formulas like this. We actually need to look at structural diagrams, which are visually how we represent the structures and organizations of the different elements within compounds. So in order to read a chemical structure, we need to understand what each of the different parts mean. So each of the letters H, O, and C, these represent the elements that a compound is made of, and as we know, elements break down into different atoms. Now, the atoms are connected with each of these lines here, and these lines, whether we have two of them or whether we have one of them like these, are what we call bonds. And a bond is simply an attraction that holds multiple atoms together. So a change to a chemical structure is a change that either involves making or breaking a new bond within a compound's chemical structures. And we can see that between the reactants and the products. We can see that vinegar, CH3COOH, has a bond between the oxygen and hydrogen atoms here, but in the products, we see that that bond is missing, which means that vinegar, CH3COOH, has had a bond broken during the chemical reaction, and we can see that that bond is actually found here in water. So we can see that water's chemical structure changes as well, because we have an oxygen that is connected to two hydrogens, but over here we have this weird looking structure of water, H3O+, that actually has three bonds, meaning that H3O+ has had a new bond that is made between hydrogen and oxygen. Now, even though we can look at these structures and we can tell that the chemical structure of both vinegar and water have changed, if you're looking at this in real life, obviously you can't see that water is H2O. We just know that water is water because it's a colorless, transparent liquid, but so is vinegar, which means that when we pour two colorless, transparent liquids together, you would not see this bond being broken and this bond being made, which means that in general, we can't always see whether bonds are broken or made. So if we can't, how do we know that a chemical reaction has occurred? The short and simple answer is we look for observations that we can actually see. And one of those, the most obvious one perhaps, is a color change. So in this case, if we look at our reactants here, we're mixing two different colorless solutions together. We know that salt, sodium chloride, dissolves completely as long as we have enough water, and salt water just looks like regular water because we don't actually see the salt. And the same is true for this other compound here called silver nitrate. We see that that is a colorless, transparent solution, just like with what water is, but then we see that this new compound here, which we call silver chloride, actually becomes white in solution because it doesn't dissolve completely in the water that makes up the solution, meaning that we can observe that a chemical reaction has happened because the reactants and products are different colors than each other. This is also an example of another observation that we can make, that being the formation of a precipitate. Now, we can see that both sodium chloride and silver nitrate are both solutions because we don't see a solid dissolved within the water, but then this new compound that we make, silver chloride, does not dissolve in water at all, meaning that it exists as a solid that forms when two proper solutions are mixed together, which means that this new solid, because these were two solutions with substances that were dissolved, this solid was not there before, and we observe that as a precipitate, and these very often are different colors than the original reactants that we mix together are. But what if our reaction doesn't actually produce a new solid? What if we see what we see in this reaction here? So if you can't quite tell what this picture represents, these are actually bubbles that are forming. Now, why would bubbles form in a chemical reaction? Well, if we do this reaction where we take a metal called zinc and drop it into strong hydrochloric acid, you will actually see these bubbles forming, and this is almost immediate. These bubbles indicate that a gas has formed that did not used to be there, and the gas that we make is actually hydrogen gas, which is exactly what we would expect, because gases don't tend to stay in liquids. They tend to rise because they have a lower density. So if we see bubbles, that means that a gas has been produced that did not used to be there. But what if what we see is not actually a new type of matter that we observe? What if we can observe a chemical reaction by looking at changes in energy instead of looking at matter? Well, if we look at this famous chemical reaction here, which is the burning of a very reactive metal called magnesium, we see that this reaction releases a very large amount of light, and we know that light is simply a form of energy. And again, this light did not exist before in the beginning of the reaction, because you can't see oxygen gas, and magnesium on its own does not spontaneously produce energy. Now, if we do this with an even simpler reaction where we take hydrogen and oxygen gas and increase the temperature by burning them together, we actually get not only water, but of course we can't see water because it would be formed as a gas, but you would actually see a miniature explosion here, which we would actually see as a small fire that only stays for a second, accompanied by a relatively loud exploding noise, and both fire and sound, again, which we would feel the fire as heat, and we would perceive the sound through our ears, indicate that some sort of change has happened, because that energy release would not happen with each of these reactants by themselves. Now, in addition to using our eyes and ears, we can also use our nose, because very often chemicals will have a different smell between the products and the reactants from which they are made. Now, this reaction here is a fairly common reaction. This is actually how we produce, or one way that we can produce, alcohol that is used in beer, wine, vodka, whiskey, as well as any other alcoholic beverage that exists. Looking for a new smell is a very common way to tell that an organic reaction has happened, because many organic compounds frequently have different scents than each other. We know what gasoline smells like because gasoline has a particular smell to it, and many perfumes as well. In fact, almost all perfumes are examples of complex organic compounds which chemists can produce, because they know that each compound is going to have a specific scent associated with them, and this is one way that we can indicate that an organic reaction has occurred. This concludes our series on introducing what chemistry is and talking about the difference between physical and chemical changes. And in the next video, we're going to explore the more foundational aspects of chemistry, that being elements, atoms and bonds and how they actually combine together in order to make the different compounds that we study in chemistry.